Hello friends, today I chose an educational video on thunderstorms, and the reason I chose this particular topic is because being a tropical country, we very often see very extreme thunderstorm events. So I decided that it will be good to kind of break down what are these thunderstorms, how they form, what are their dynamics, and what kind of basic things we need to know in order to predict these events. And these are very localized events, so that's why it is not easy to predict them, and they also cause some localized damages as well. Hence, it's a very important aspect from a tropical country's viewpoint. So let me start with the basic definition. As I already said, these are very dense localized cloud masses, and sometimes we call them as cells or supercells, which are known to give short duration extreme rains along with thunder and lightning. So the thunder and lightning makes it even more dangerous because it can lead to loss of life. Not the rain as much, but the thunder and lightning is the most dangerous aspect of these thunderstorms. And the supercells, which are the massive thunderclouds, if they grow beyond some size, then we call them supercells. They are known to produce hail, and this we usually refer to as hailstorm, which is a kind of a subset of a thunderstorm. The mechanism of formation of these thunderstorms or hailstorm is pretty much the same, which I'll talk about later in this video. The thunderstorms bring along with them very gusty winds. So suddenly you will see that there is a strong winds for a short period of time. That is because of the formation of these thunder cells. And because of this, they are also colloquially called as meso-cyclones. The reason we call them as meso-cyclones is because they are a very localized, rapidly rotating mass of air, whereas a cyclone is a much synoptic scale system which goes all the way to 500 or thousands of kilometers wide, whereas a mesocyclone is something which extends up to 20, 30, or maximum 50 kilometers. So that is why these are also known as mesocyclones, because they are kind of they have a very similar imprint as that of a cyclone, because they are highly localized rotating mass of air. The only difference is that the Coriolis force doesn't come into picture for these mesocyclones, and secondly, the movement of them is not as complicated as the cyclone, where cyclones move along a ridge, whereas these mesocyclones have a very different kind of movement, which I'll talk about later. Okay. So the only reason they are called mesocyclones is because of the rapidly rotating mass of air parcel. There are many different types of thunderstorms. The first one is the frontal storm system. So what is a frontal storm system? When a cold air undercuts warm air. So let us say a cold air is blowing and it kind of sweeps into the ground, and that results in the warm air which is next to it or adjacent to it. Since the cold air is moving, the warm air is lighter, so it gets lifted up or it gets advected upwards. And due to the moisture difference, the warm air is moist and cold air is dry, so they mix with each other and they lead to formation of these supercells or thunder cells. And this basically cold air undercutting warm air is known as a cold front, and this usually occurs when the sea breeze sets in after a very warm day, and leading to formation of thunder cells. And this is a typical mechanism of formation of thunderstorms in a coastal area like Mumbai or Goa or Chennai and those places. So the thunderstorms that you see around these coastal regions are basically due to a frontal system. Then you have something known as a convective system or convective storm. This basically happens because the ground heats excessively, and that leads to localized updraft, resulting in formation of thunder cells. And this is a highly localized mechanism because you have the strong updraft because of the heating at the ground, and the moisture is going to come in from the ocean. So the winds have to penetrate all the way to the interior districts, and that leads to formation of these convective storms. Sometimes what happens is, you must have seen on radar images or satellite images, that small pop-ups in many places, then they kind of merge to form a chain of thunder cells. And then later on what happens is they are advected by the upper level winds, and this leads to a widespread thunderstorm activity. So there could be many small pop-ups which don't seem like very intense storm activity. But then what happens is due to conducive conditions of wind direction, or the winds which are upper level winds, which if they are strong enough, then they will lead to formation merging of these small pop-ups or small cells, and then you can have one massive cell which will just give you a widespread thunderstorm activity. So this is the basic types of thunderstorms. These are the basic types of thunderstorms. So this is exactly what I'm talking about. The sea breeze sets in. As the sea breeze sets in, you can see that it the sea breeze is coming in from the ocean to land, and that kind of leads to the warm air moving up and formation of these thunderclouds, which gives rains to coastal region. This is the reason why Mumbai gets only thunderstorms just before onset of monsoon, when the sea breeze is strong, and also during the withdrawal phase. The sea breeze has to be not very strong, because what will happen is the sea breeze will just penetrate inland and it will not allow for the formation of thunderclouds very close to the coastal region. That's why most of the time interior places get a lot of thunderstorms, because the winds usually meet in the interior places. Whereas this is the localized, where you have the strong heating which leads to a vortex kind of a mechanism, and it leads to these tall cumulonimbus cloud formation. So you can see the difference in the mechanism by which coastal region get thunderstorms, and the mechanism by which your interior places get thunderstorms. It's because of this ground heating, whereas this is more like a frontal system. The dynamics is pretty much the same, whatever type of thunderstorm it may be. So there is something known as CAPE, which is convectively available potential energy, and there is something known as SIN, which is convective inhibition. So this is a little bit mathematical, but let me try to explain it in simple terms. So what happens is you have two things here. One is a parcel, other is environment. So what happens, generally a parcel is a moist or dry parcel of air which rises up in the environment. So what can happen is two things can happen. If the air parcel that is rising is warmer, then it will keep rising up because environment is colder. So it has more buoyancy, so the parcel will keep rising up. Or the second thing that can happen is the parcel is colder, so it will just stay put and it will not rise up. And that is the SIN. So SIN is basically the convective inhibition. So the environment is at a larger temperature than parcel. So the air parcel, or the moist air parcel which is trying to rise up, doesn't go up because the environment is not allowing it to move up, because the parcel is colder, whereas the environment is warmer. You have to reach a level of this free convection above which uh, you can have the cape kick in, and that leads to formation of thunderstorms. So what is needed is higher cape is of course is required, because higher cape means the parcel has the potential to go to higher levels and form tall clouds. But the other thing is lower SIN. So the SIN cannot be very high, in the sense that the environment cannot be at a very large temperature for a very long distance in the vertical direction. So the SIN has to be very small, because that the parcel has to move up. It has to cross that particular threshold, so that you get to this level of free convection, and then the cape takes over and does its job. Okay, so during winter time this is not possible. Thunderstorms are not seen during winter time, because our parcel is colder, whereas the background atmosphere is warmer. So always you have these fog or smog lying around at lower levels, and that means that it has not allowed the parcel to rise to a very large degree, okay, thereby not allowing the formation of tall thunderclouds. Okay, so this is the difference. Like the SIN has to be very small, so that means this region, this dotted region that I'm talking about, should be very small, so that the parcel which is heated up because of the ground can break this barrier, and then it can just go above this level of free convection, and it can start forming these tall thunderclouds that are known to give very massive thunder storms. Okay, so the two things again which are important from a dynamics point of view is cape and SIN. So SIN has to be small, in the sense that the amount of stratification that I'm talking about. So the background cold air in the environment should not be much. It should not have. It should not be too much warm, which will inhibit the parcel to move up. The parcel has to move up, because only once it moves up, it can lead to formation of the cloud condensation level, and then from there on, it can lead to the formation of these so-called tall clouds. So let us look at the anatomy. The anatomy is as follows. There are many different terminologies here, but the main thing is this is not a frontal system. I am talking about a interior thunderstorm, which is mainly due to the localized heating. So the ground heats up, the parcel gains potential energy, so it is warmer. Atmosphere is background atmosphere is colder, so the parcel will keep rising up, okay, upwards, and it will break the SIN barrier, or the SIN, which is the convective inhibitive inhibition. So it will cross that. After that, it is just free to flow because it has crossed that limit. And then after that, the temperature of the parcel is always greater than that of the background atmosphere. Okay, so it will keep rising up, and that means that the cape is also higher, and that cape will ensure that you have these tall clouds which are forming. Uh, the place where the SIN is being broken up is known as the lower level of condensation, because that is the base of the cloud usually, and that base of the cloud is where the SIN barrier has been broken, and after that the cape takes over, and the cape ensures that the clouds grow much taller, uh, as large as 10 kilometers, 12 kilometers, or sometimes 16 kilometers tall, and that's what you call as these mammotus cumulonimbus clouds, or cumulonimbus congestus clouds, or towering cumulonimbus clouds with anvil and all those things. Uh, but the base of the cloud is the parcel has to break that barrier. Otherwise, what will happen is you cannot form these tall clouds. What will happen is you will have a very low, shallow cloud, which is basically fog. Okay. The second thing is, as the parcel moves up, it is being sheared because of the wind. So the winds will move it up, right and left. So the parcel will gain angular momentum, and that angular momentum will ensure that it has this spiral kind of a vortex pattern. It means it will keep circling around, and that is how it attains this rotational pattern. That's why we call it a meso-cyclone, because it keeps getting this rotational pattern, and that rotational pattern is what gives it the mixing. So if I'll give you two things here. Assume that a parcel is just simply rising up, versus a parcel which is creating this kind of a mixy phenomenon, if you may, that the mixer is kind of rotating, right? If if you want to grind anything, then you mix it, correct? In a mixer, you just turn on the knob and it will create this rotational pattern. What the rotational pattern actually does is it brings the moisture inwards, and that moisture is what is very important for formation of these tall clouds. If this parcel was just rising up in a straight line, then it is not very beneficial for thunderstorms. It has to kind of have this angular movement, which is this rotational movement is very important. And this is not coming from Coriolis, because this is a localized activity. Coriolis doesn't have the capability to affect thunderstorms. This is basically coming from this the shear that is present inside these tall clouds, because the winds are very strong, and these winds keep circling this parcel, and that's how this rotational energy, or the rotational pattern, or the angular momentum is coming in, and this rotational pattern is what gives it the amount of mixing that is needed for these tall clouds to form. Okay, so I hope it is very clear. One other thing, the important thing is this flanking line. This flanking line is nothing but the line at which the wind starts coming inwards, or the updraft starts happening, and this is the widespread region where we will have these strong winds coming in and trying to sweep in the parcel upwards. Okay, so that is this flanking line, and the flanking line is always present at the ends of the thunderstorms. Okay, because that's where the updraft is kind of initiating. Okay, and after the updraft happens, the tall clouds form, and you have this downdraft, which is basically heavy rain or hail. And once this entire moisture is being advected downwards, or entire moisture has been taken away from the cloud, then it will automatically die its natural death. So what is the killer here? Deep moist convection. Deep moist convection, as I talked about, as the air parcel rises, it cools, and the air parcel is not moving straight. I already talked about it. Keeps on moving in a rotational manner, creating this vortex pattern, which is what we call meso-cyclone. So this parcel keeps bringing in a lot of moist air, and as it goes upwards, the water vapor cools, and at the same time, because of the cooling, it gains latent heat energy, because there is a phase change, and the latent heat energy is instantaneously released when the saturation happens. That is, the vapor becomes droplet. So what happens here is, somewhere at this location, the vapor has converted into droplets, but even after converting to droplet, the droplet doesn't stop moving. It keeps moving upwards, and as it moves up, as the latent heat energy is released, the droplet keeps moving upwards, and at some point it will come to a standstill because of the because the density of the droplet and the atmosphere in which it is in is the same, and that is uh, um, that is the reason why you have these formation of towering cumulonimbus clouds, because the latent heat is released, and it allows the parcel to reach much longer heights, and that's what results in the formation of these anvils or these mammotus clouds that we talk about. At some height, the pressure is zero, so the parcel will freeze, and that results in the collision of crystals, resulting in thunder and lightning. Because because there is a lot of turbulence, right? Because there is a lot of rotation inside the thunder cell, um, and because of the turbulence, the parcels will collide with each other, and the parcels will grow in size. And once they grow in size, they will fall under gravity, and they will just fall down as hail or rain. But because of the collision, the charge transfer occurs, and because these are charged particles, that's how you get thunder and lightning. Some tidbit: a rule of thumb in operation meteorology exists that for non-mountainous region, I'm not talking about mountains, in a non-mountainous region in a flat plain, to determine if the SIN, which is the convective inhibition, is strong enough to cause a thunderstorm. Uh, this is possible if a thunderstorm is not possible if 700 millibar temperature. So 700 millibar is around 3 kilometers from the ground. So the temperature of the environment at 700 millibar or 3 kilometers from the atmosphere, from the ground, is, if it is warmer than 12 degrees C, then it is likely that the thunderstorm will not occur, unless some mechanism which can cool this temperature, and that mechanism is basically frontal lifting or mechanical lifting by mountains, wind convergence, basically some cold air is being converged upwards, or a mid-level instability like a 500 millibar cold air is rapidly dropped down, so which results in instantaneous cooling of the atmosphere, and this will allow the parcel to rise up. Because everything that is needed is the SIN has to be broken, the convective inhibition barrier has to be broken, otherwise a thunderstorm cannot form. Okay, this is the basic of a thunderstorm. Unless the SIN is broken, cape cannot kick in. So this is a very so people only look at cape, people don't look at SIN, and that's not right, because cape can only kick in after the SIN has been broken. The convective inhibition potential barrier has been broken. So for that to break, you cannot have atmosphere at a much higher level, at a higher temperature than the parcel, because the parcel cannot move up. Okay, so this is a very very important aspect which many people miss, and hence the prediction go haywire. The stages: initiation is basically the breaking of the SIN, growth because of the cape, the convective and potential energy. Dissipation is once the cape has kicked in, then anvil forms, and once there is enough collision of particles, then big raindrops or ice crystals form, and that's when you have rain. And once all the moisture has been sponged out from the cloud, then the cloud dies its natural death, and that's the dissipation stage. Prediction is basically ground-based convection. How much is the heating? Is it enough to break the SIN? That's very important. So we need to look at the parcel temperature and the temperature profile of the background, which is the atmosphere. If they are not conducive, then we have to check the wind convergence or a cold front development, or a possibility of a mid-level instability that will bring the cold air down, allowing for the SIN to break. And generally the SIN breaking level is seen at 950 or 950 millibar or 925 millibar level, because if the SIN is very strong at these levels, then there is absolutely no possibility of thunderstorms to form. Moisture incursion: check the humidity levels. If the humidity is very high, then of course there is a lot of favorable criteria for deep moist convection, because the cape values will be high, because there is a lot of moisture which will bring in a lot of latent heat, and this is crucial for formation of supercells. And of course, check the 700 millibar temperature. If it is higher than 12 degrees C, then thunderstorms cannot form. It has to be lower. These are some basics that if you are interested, if you are a weather enthusiast, please follow these basic checks. There is much more to this. I don't want to get into the depth, but these are the basics. If you can't get the basics right, then I'm sorry. This is all about thunderstorms. I hope you had you gained some useful knowledge. Thank you for the support, and please subscribe to the channel for regular weather updates along with the dynamics. Thank you very much. I will see you again with the next video, which will be on some other topic.